All right, good morning. Welcome back. If you have your project report, you can set it here, or otherwise we can do it towards the end of the class. All right, it is due in class, so after this I won't be accepting these reports. So make sure if you have not given it to me, give it to me after once the class ends. All right, any questions before we start? Okay, so I want to start with actually discussing the programming assignment, programming assignment 2. Just sort of go over it. I really like that assignment. It just gives so many insights, and I hope you appreciated all of those. But if you haven't, I just want to go through it a little bit so that we have a similar understanding. So let me bring it up. Because I noticed some questions on Piazza as well about why things were happening the way they were happening. So I thought it'll be good to sort of talk about it. All right, so let's not worry about these parts. But okay, so of course there were multiple parts to this assignment, right? So the first one was about QDA versus LDA, and I saw that a lot of you got it right. It's not a very tricky thing to solve, but the last thing that I wanted you to see was these boundaries, right? So LDA and QDA, linear discriminant analysis and quadratic discriminant analysis, are very similar to each other, but for one difference, which is that in QDA you have the same, you have different covariance matrices, whereas in LDA you have just one, right? And the effect of them is pretty significant, even for this very simple data. This was fairly simple, right? You had 5 classes. They're pretty good in terms of separability. So you were able to, even LDA, and I mean the accuracies that you got were pretty good. And when you sort of plotted these boundaries, the difference that you got was that LDA was giving you linear boundaries and QDA was giving you quadratic boundaries, right? And that, so the question to be asked here is why? Why was this happening? So let me quickly talk about it, try to show you why QDA gives quadratic, LDA gives linear. The reason for that is because that helps you understand when you make these different choices, right? The choice seemed to be pretty sort of a very simple choice. Okay, let's use covariance matrix that is common to all classes, or will you use covariance matrix which is one for each class? But the difference that comes because of that is very interesting to see, right? So let's see. So of course this is just a general discussion, right? So remember, so LDA versus QDA, and we are trying to understand, okay, why does QDA give quadratic, LDA gives linear? Okay, so the reason is this. Now remember, in both of them, what you are trying to do is for a given data point, you are trying to find two quantities, okay, Q1 and Q2. Q1 is the probability that Y is class 1 given X is X star, or whatever test input, and Y is class 2 given X is X star. Here I'm assuming it's a binary classification, but later you can generalize it to 5 classes as well. But this is these are two quantities that we want to identify, right? And then what we do is whichever is minimum, whichever is maximum, we choose that as our probability, right? So this is true for both QD and LDA. And then what we do is this we apply Bayes rule to that. Given Y equal to 1 divided by some quantity, which is, I'm going to call it Z because it's common to both, right? So we don't really need it, right? And then for this assignment, what I did was I said, you know, forget about these parts because the classes were equally sampled. So we ignored the posterior, and then we merely computed this, right? But what you will see is that these quantities, they do not have any X in it. They don't depend on X, right? So even if they are there, the whole sort of just this explanation would still hold. But for your assignment, what you did was you essentially computed these two things. P X equal to X star, Y equal to 1, and P X equal to X star, Y equal to 2 for binary case, right? Okay. Now, let's talk about QDA. So in QDA, what you did was you said that we are going to assume that this probability is actually a Gaussian, right? And so we can replace this with the PDF of a Gaussian. And one thing I'm going to do is that I'm going to say that this is equivalent to saying log of this, because that's easy for me to do the math, because you can either compare the probabilities or you can compare the log of probabilities. It'll give you the same answer. So let's look at what this is going to be. So Q1 is going to be log, so when I expand it, if you remember all the expression for the PDF, right? So it's going to be log 2 pi minus d by 2, or d by 2 can come here, minus log of determinant of sigma half, right, minus 1 by 2 x star minus mu 1 transpose sigma 1 x star minus mu 1, right? And because I just took the log of the PDF, and Q2 is the same, sigma 1, this is going to be sigma 2, the log of the determinant, and x star minus mu 2 transpose sigma 2 x star minus mu 2, right? So these are the two quantities that you compute. Okay, so now let's sort of expand this part a little. Now what you see is that these two components here, they are independent of x, right? There's no x inside that. Basically what I'm trying to show here is that the dependence between q1 and x, because that will determine what will be the shape of your curve, right? Because you're plotting your curve based on q1 and q2. You're saying whichever is higher, I'm going to call it that color. And what we really want to see here is what is the dependence of q1 and q2 on x. These quantities don't have x, so I'm going to ignore that, right? So we'll just say that here we're trying to q1 prime, and this is just x star minus mu 1 transpose sigma 1 x star minus mu 1, and q2 prime inverse as well, right? Sorry, x star minus mu 2, right? So these are the two things that we want to apply, right? So now let's do it for a simple case, a simple scenario. Let d be 2, which means that, which is actually true for your programming assignment, is that let's say there are only two elements in your x's. So these are all vectors. X is a vector, mu 1 is a vector, this is a matrix, right? So in this case, x star will be a column vector with, let's say, two values, x1 and x2, right? So these are the two dimensions. Mu 1, let's say, is also going to be a vector. So this is the first mean vector. Let's say it has two components, mu 1 1 and mu 1 2. Mu 2 is mu 1 2 1 and mu 2 2, right? And then sigma 1 is a covariance matrix, and let's say this is, or sigma 1 inverse, right? Let's say this is just E1 1, E1 2, E1 3, E1 4, right? It will have four values. It could be anything, but let's say we're going to express it like this. And sigma 2 inverse is E2 1, E2 2, E2 3, E2 4, right? So this is for this simple example, right? So now let us try to compute what Q1 prime and Q1 prime are going to be, right? So Q1 prime. So Q1 prime is here, right? So this is okay. Let's first write. So what is x star minus mu 1? It is going to be a column vector, which is x1 minus mu 1 1, x2 minus mu 1 2, right? And x star minus mu 2 is also going to be a column vector, which is x1 minus mu 2 1 and x2 minus mu 2 2, right? That is easy. So now let's, equipped with all of these intermediate values, we can compute what is Q1 prime. So Q1 prime is going to be this transpose, right? So that is going to be a row vector with x1 minus mu 1 1 times x2 minus mu 1 2 multiplied by our sigma inverse, which is E1 1, E1 2, E1 4, and then this column vector, right? And now what you can do is you can actually multiply it. So this is a 1 by 2 vector multiplied by a 2 by 2 vector, right? So matrix multiplication, you multiply first row with first column, that will give you the first element. So it will become x1 minus mu11 times e11, right? The first row with this one, plus x2 minus mu12 times e13. So that will be the first element of this vector, and then this row with this column. So that is x1 mu11 into e12 plus x12, sorry, x2 minus mu12 e14, right? So this will be when I multiply this times this, and then this part will still hold. Yeah, and now so this is a vector, 1 by 2 vector, and this is a 2 by 1. So then this will give you a number, right? So 1 by 2 times this is 1 by 2, this is 2 by 1. That should give you a scalar value, and which is essentially a dot product. So this times this plus this times this, right? So it is, and so when I multiply this with this part, that will just be x1 minus mu11 square e11 plus x2 minus mu12 into x1 minus mu11 e13. So that will be the plus this this times the second one. So x1 minus mu11 x2 minus mu12 e12 plus x2 minus mu12 square e14, right? So this will be the whole q1 prime, right? And then you can also compute q2 prime in the same way, except that instead of mu11 it will be mu21 and mu22 and so on, right? But the thing that I want you to understand is that q2 prime will be something, right? So if you just compare them, what you will see is that in this whole expression, right, you will have a quadratic term in x1, right? Because it will be x1 square minus 2 mu11 x1 times something. So q1 prime will have x1 square and x2 square inside, right? Because there is a square term here and a square term here. And same way, if you work out the whole math, q2 prime will also have, which means that these are quadratic in your data, right? And that is why you get a quadratic boundary, right? But what happens with LDA is, in LDA, things are very similar, except that your sigma 1 is equal to sigma 2 is equal to some sigma, right? Which means that your E11, E13 is equal to E21, okay? Which will mean that when you expand these terms, right? So when you write out the, so let's ignore the the non-quadratic terms, but in q2 prime you will have x1 minus mu21 square e21, plus you'll have all these linear terms, plus the same thing like here, x2 minus mu22 square e24, right? But since e24 and e14 are the same, that means that these two quantities will be the same, right? And since e11 and e21 are going to be the same, that means these quantities are also going to be same. That means that the quadratic terms are going to get cancelled out, right? So when we compute in LDA, so the q1 prime for LDA and q2 prime for LDA will not have, or will have the same quadratic term, which means that they do not have any effect on determining which one is larger, which one is smaller, right? So that means that their effect won't be there. That means so you will just be working with the linear terms. The linear terms will not go away, right? Because here, of course, E13 will be the same as E23 here, but since x2 gets multiplied by mu11, x1 gets multiplied by mu12, which will be different, which means that there will still be something to compare against. And that is why when you do your QDA versus LDA, you see an effect like this, right? LDA gives you linear boundaries because it has no, when you do the comparison, there are no quadratic terms to compare against, whereas in QDA, the quadratic terms also have an effect, right? And that is why you see this. Any questions? All right, very nice. So for those who just came in, what we are doing is just going through the assignment, trying to tease out some interesting insights from this whole exercise that you did, right? Another thing that you can see in LDA versus QDA, and this is very marginal, but the performance of QDA was slightly worse than the performance of LDA. And this is a very simple data set, right? So anything should work. But even here, you can see that, and the reason for that is that QDA is trying to do more, right? It's trying, LDA is simpler, there are lines. So in terms of our VC dimension discussion, the VC dimension of QDA will be larger. That means that it has a more tendency to overfit. So that's what it is doing here. It's able to learn a pretty good classifier, but not as good as LDA because it's not able to generalize as well as LDA does. All right. So that is another thing that you can look at. The second problem, it was similar. I mean, all you needed to do here was regression. But even here, what you can see is that this effect of intercept, right? We always talk about incorporating the bias because we want the line to not go through origin. And that's what's happening here, right? When you try to fit a line without adding the bias term, what happens is you're forcing the line to go through the origin. So you might not get a very good fit. And that's why your error is much larger than when you add a bias, right? That was the only thing. Ridge regression is fairly easy to understand, right? Ridge regression, you're trying to regularize your coefficients. So clearly what happens is that when so if you remember your ridge regression objective function, there is an error term, and there is a regularization term, right? So if you focus a lot on your error term, your training error will be low. And so here in this plot, this is when your lambda is 0. So lambda controls the effect of that regularizer. So here there is no regularization. So your error is pretty low, right? But when you apply it to test data, your error is actually higher. So that is this notion of poor generalizability, right? However, as you regularize it more, there comes a time at which even though you are accommodating a higher, or you are incurring a higher training error here, you are actually getting a pretty low test error. So this is basically that optimal point at which the curve, or at least the weight vector here, is regularized just enough. Okay, and then of course, if you regularize it too much, then error will start going up again, because now you are basically saying ignore the training error and just focus on making the L2 norm as small as possible. That was that. The problem 4 was just simple, just using minimize instead of this. One thing that you can notice here is that when you do minimize and you only let the minimizer run for 20 iterations, then you get a little irregular curve, not as smooth as what you get from a direct minimization. However, if you increase the number of iterations, you must have seen that you would be able to smooth it more. The reason for that is that when you're setting your maximum iteration to 20, essentially what you're saying is that in your gradient descent, you are forcing it to stop after 20 steps, which means that it might not have reached the optimal value, right? So that was the issue. Problem 5, now this is my favorite, right? So this is where you took just one feature, right? And you said, I'm going to just use that as my feature, but I'm going to do basis function expansion of that, right? And there were two versions here, one in which you didn't do any regularization, so you increased the complexity of your curve. So 0 is, of course, you're just learning a flat line, but 1 is your linear regression, 2 is a quadratic, 3 is cubic, and so on, right? So what you see is, if you only look at the blue lines first, is that as you increase the complexity of your curve, your error goes down. Now this data is relatively simple because there's only one feature here, so you don't see too much a drastic drop, but in real data sets this would be more drastic. So as you increase the complexity, you're making your curve to be more nonlinear, so it sort of tries to follow the data a little more, but your test error actually goes up. So this is again this case of poor generalizability. You made your solution too complex, and even though your training error was small, your test error shot up, right? However, when you do regularization, now even though your training error is slightly worse than when you didn't do any regularization, your test error actually gets pretty good, right? So which means, so what happens here is that your solution is still non-linear but not too complex, right? So that is the whole beauty of this thing. All right, any questions? Cool. All right, so let's move to our discussions about what we were talking about last class, which is logistic regression. Thank you. Well, I think we pretty much did logistic regression, right? So let me just do a quick recap. Logistic regression falls under this general class of generalized linear models, where you relax this link that y. So in linear regression, y is normal distribution W transpose x. In logistic regression, y is a Bernoulli with parameter as sigmoid of W transpose x. I don't know if anyone got a chance to attend. There was a talk yesterday from this guy Sharad Chikkarur from Boston, who works for this company called Nanigans, which is a company that what does it do? It deals with these online ads, right? So they're like stockbrokers. So they, on behalf of companies, right, like let's say Uber or CNN, they put ads on Google or Facebook and so on. So CNN gives them money and says, here are our ads, put them in the most optimal locations in Google and Facebook so that it maximizes our revenue. So when he was talking about everything, he mentioned a lot about using linear regression and logistic regression for their tasks. So they use a lot of very simple machine learning algorithms to drive their business. It's a pretty big company. It has a lot of business. He's talking about like they move around billions of dollars a day in terms of advertising revenue, right? But anyway, so that was just a side note. But okay, so logistic regression was this. It was simple to work with. There was a log likelihood function that we know how to maximize, right? We know how to do gradient descent. Then I talked about Newton's method, which is slightly improved version of gradient descent, in which you use a Hessian to control how to move in every iteration, right? And talked about the Hessian as well. Also talked about the regularization, which is kind of like ridge regression, but with logistic regression. You can also do L1 regularization, so like lasso for logistic regression. And this is also similar to putting a Gaussian prior. This is something we have seen before, right? And then there was this issue about what if instead of 2 classes, we have multiple classes? And it turns out that logistic regression is very well set up to do that as well, except that your theta is no longer now model a Bernoulli, but it's actually a multinulli random variable, which means that it has k probabilities in a vector theta, right, which are defined like this. So we can do all of that. And then I talked about Bayesian logistic regression, where we said that instead of just getting the MLE estimate for W, what if we want to get a posterior distribution for W, because that's what we do in Bayesian logistic regression. And we quickly came to the conclusion that it's not easy because the integration becomes very difficult. If you're not following this, just refer to our last class discussion, right? So there is this issue that when you're trying to compute the posterior, you can always write the posterior's equation, right, using Bayes' rule. There's no problem with that. But when you go to actually solving it and getting some closed form solution, it becomes very intractable if your integration is not good. So any time when your prior and your likelihood are not conjugate of each other, then it is very hard to get the posterior, right? And then we looked at one way to approximate the posterior and I went through the whole thing, which is how do you approximate the posterior, knowing the map of your posterior. So we already know how to compute the mode or the most likely value for your posterior, but we don't know what the posterior is. That was the problem, right? So you can get the mode by solving this regularized, where is that? Here, regularized equation. This will give you the W map, right? However, what we don't know is how to get, what is that posterior distribution? Is it a Gaussian? Is it a gamma distribution? We don't know that, right? So what we do there is that we assume, we sort of do an approximation. And it turns out that when you do this whole approximation using Taylor series expansion, you can get, I'm quickly going through, I did that last time, so you can refer to those notes. But basically, you can figure out that your posterior for W after observing D can be approximated as a normal distribution, all right? And the map that you get by solving the regularized formulation is the mean of that posterior. And interestingly, the covariance matrix is nothing but the Hessian of your objective function at map, all right? And we know how to compute both of that. So that is the whole beauty of this, all right? Now, of course, the second question is, once we have the posterior, what do we do with that, right? So if you go back to many weeks from now, when we were talking about figuring out the parameters of a coin toss, the theta, right? So we did MLE, we did the sort of this posterior version, and then we saw that we can use this posterior in two ways. We can either use the map of that posterior, or we can do Bayesian averaging, right? In this case, map, of course, we already knew the map. So why would you compute the posterior to again get the map? In fact, we use the map to get the posterior, right? So we don't, if you just want to use map, then no need to do this Bayesian process, this approximation. But if you want to do a Bayesian averaging, right, that is the case where you would have to do something more, because the problem becomes a little more trickier there. So remember, here it is, right? So now you want to get a prediction for a new x. You want to find what is the probability of y to be 1 or 0, right? And in Bayesian averaging, what you do is you say, I'm not going to assume one value for w. What I'm going to do is I'm going to use all possible values of w, and I'm going to weight them by their probabilities, right? So this is something that we have talked about many times. It turns out that solving this integration is very difficult, right? So remember, Pw given d is a Gaussian, which is given by this. So I know the PDF of that. Py given x comma w is a Bernoulli distribution, which is theta raised to 1 minus theta raised to yi 1 minus theta raised to 1 minus yi, right? So we know the expression. So we can actually write the mathematical formulation here. But the problem comes, how do we integrate it, right? We are not, as human beings, we are not very good at integration. Differentiation, we know. Integration, we like to sort of avoid it. And we can do it for simpler functions, but not for functions like these, where a logistic sort of expression is getting multiplied with a PDF, right? So now how do we compute this? Because we still need it, right? So one way to do it is this class of methods called numerical integration. So some of you might be familiar with that. So numerical integration is useful if you don't know how to compute the analytical integration, right? So in this case, it actually becomes a little more easier, and this is what we call Monte Carlo approximation. And this is not really part of this class, but I just want to give you a brief flavor of this, because you might encounter this in future. So this is how sort of these inferences, so this is inference, right? So you are trying to get the y given x, and we have been doing that for linear regression. But in linear regression, because the form of our probability model is very simple, so y given x is just w transpose x, a normal distribution there, you can get y, right? It's very easy. Same thing with naive Bayes or QDA, LDA. But when models become complex, when all of these probabilities are more complex than just simple PDF of a Gaussian, then computing this becomes the most important task, right? And this is where we need to figure out some approximate ways to do this. And that general technique class of methods is called approximate inference. So you want to infer y given x. You cannot do it in an analytical way, so you want to do it in an approximate way. And one way to do that is what we call Monte Carlo approximation. So just in 1 minute, I want to give you a brief flavor. So remember, what is integration, right? So integration is nothing but you're given some curve and you want to find the area under the curve, right? So if there are bounds, so if this is fx, then it is just computing the area between a and b. However, if it is, from minus infinity to infinity, then it is just the area under the whole curve, right? And the way we do it is by saying that, let's create these very thin rectangles of size dx each, right? And then compute the fx at that value, multiply that will give you the area of the integral, area of this thin slice of rectangle, and then we add it up, right? And as long as your dx is very small, then the limit of dx tending to 0, the value that you get will be equal to the integration, right? So that's just the math. But how do we do it in this case? So here what we have is we have some function of x, and then that gets multiplied with some distribution of x, dx, and this. So this is what we want to compute, right? In a simple way, of course, for Bayesian or Bayesian inference, the exact equation looks like this, right? So this is what we want to compute, but I'm assuming that instead of, okay, let's just write w here. So this part can be treated as a function of w. This part is the probability of w, and this part is dw, right? So this is what we want to compute. Now, how do we do that in a approximate way? This is what we call Monte Carlo approximation. So here what we do is we sort of do a loop, okay? So we'll have some s will be 0. Then for n iterations, or w is a sample, because we have this distribution, right, from p of w. So we know how to draw a sample from this. So we draw a sample, and the probability of w will be given by p of w. So you will get more w's around the mode, right? And then s becomes s plus f of w, right? So what you essentially do is you repeatedly draw samples from this distribution, which is given by pw, and then you compute f of w for that, or in this case this value, and then you keep adding that. So what the effect of this will be, for large enough n, right, f of w, pw, dw, this integration will be very close to s. And I mean, think about it a little more, but I mean, this is all I want to talk about. But the idea is that you are favoring those w. See, ideally what you would have to do is you would have to find each w, and for each w you want to find this fw and keep adding it, right? So that's the integration, right? But we don't want to go from minus infinity to infinity. That will take us longer than we want, right? So what we do is, instead of doing that, we say let's just pick the w's which are more likely and just compute, because f of w is getting multiplied with p of w, right? So if there is a w which is not very likely, then even if we had that f of w, since that would get multiplied with that low probability, the effect of that on this overall integration will be small, right? So as long as we are picking up more likely w's, the p of w's for those will be high enough, which means that they would have a more effect on this. So that is why this holds, right? So this is a general flavor of Monte Carlo approximation, and maybe I will give you a little bit of exercise to practice this more. Any questions? Yes. how do you pick, oh, I see, so this step, this sampling, right? So what you're saying is, how do we get these samples? So here, basically what we have assumed is that we have this distribution, right? So we have this distribution. So let's say so in the case of logistic regression, we are assuming this is a normal distribution, right? Which means that every distribution, there is a capability of drawing a sample, right? Because that's what the property of a distribution is, that it can generate a sample for you. So because you are sampling from that distribution, which means that it will more likely give you values that have higher probability according to that distribution. Any other questions? Excellent. So that kind of concludes the whole discussion on logistic regression. And now I'll move on to the next topic, which is related to this. So it's not a huge jump. So we're going to talk about something. Oh, sorry. So this is part C3, maximum margin method. So I don't know how long we'll get today, but the idea here is that we are still sticking to linear models, right? So we have so far looked at 4 linear models in our whole course, right? We have looked at perceptrons, we have looked at logistic regression, we looked at linear regression, and now we are going to look at this 4th one, right? Let's ignore linear regression for now. So the commonality between perceptron, logistic regression, and support vector machines that we're going to look today is that they're all classifiers. Linear regression is a sort of, it predicts a value. So let's keep it aside. And it turns out that all of these 3 classifiers are very similar in how they predict, right? In fact, Ritvik had pointed it out last time that if you look at logistic regression, right? Regression, and let's look at perceptron, right? So in both, so in perceptron what happens is that you have some W, right, and you get some X, you compute W transpose X, right, and then you say if W transpose X is greater than 0, then Y is 1. We assume that X has the bias term as well, so if Y is 1, else Y is 0, right, or 0 or minus 1. In logistic regression, what we do is we say if sigmoid, right, so 1 over 1 plus E minus W transpose X, right, if this is greater than 0.5, so this is the probability of getting a heads, right, then Y is 1, else Y is 0, right? These are the 2 different decision functions. But if you work this out, what you will see is that this is same as this, right? Because if I take this here, half here, take a log of this and whole thing, right? So this could be 1 plus E power W transpose X is less than 1, so 2, right? And then this goes here, so 1 is E power minus W transpose X, take log on both sides, this will be 0, greater than minus W transpose X, which means W transpose X less than, greater than 0. It's the same thing, right? So if W transpose X greater than 0, then call it 1, otherwise 0. So they both are the same. And I think we discussed last time is that the difference is how they find the W. So it's not how they predict using W. Prediction is the same. They both use same kind of approach. And it turns out that the method that we look today is SVM, has the same decision rule. So it also has a W, right? And it looks at, okay, is W transpose X greater than 0? It calls it positive, else calls it negative. The difference being, how does it, the difference between logistic regression, LR, perceptrons, and SVM, they have same decision function, but different learning strategy. Okay. In fact, LR and perceptrons, logistic regression and perceptron, had a very similar strategy, right? In both, you use gradient descent to either minimize the squared loss or maximize the likelihood, right? But it turns out that the difference is that in one you are using a squared loss, and another one you are using, if you convert that likelihood into an error, basically you are trying to minimize a log error, or log loss, so that loss are different. But what SVM does is slightly more interesting. It does something little different, and that is why SVMs, at least before sort of all this deep learning, were very popular, because they did something that was much more interesting in terms of how they would control the ability to generalize better than logistic regression and perceptron. So we'll look at it now, right? But before that, we are going to do a little bit of geometry, which we love, and also introduce some notions. So in the case of SVMs, I'm going to not add that one into the as a bias term, okay? So I'm going to treat the bias separately. It's easier to explain, okay? So in SVM, we are going to assume that the decision function looks like this. So the line that we learn is W transpose X plus B, which is same as W transpose X if your bias, if you had a 1 in your X, right? Then B would become the last element. But here we are assuming that bias term is being held separate, just so that I can easily understand, sort of explain it. Okay. Now comes the question: is what is the difference between perceptrons and SVMs? Okay. So for that, let's go back here. So let's say this is my training data. Okay. So I have two types of points. I have these. Already drew this. Triangles, and I have these circles. They are linearly separable, right? Which means that if I train my perceptron, it will give me a line which gives 0 training error, right? But the question is, what line will it give you? Because this is a correct line, but this also could be a right line, and this could be a right line, this could be a right line, and this could be a right line. So there are infinite possibilities. If your data is linearly separable, you can draw infinite lines in that space, and all of them would give you 0 training error. So the question is, which one will perceptron choose, right? In fact, even for logistic regression, it's the same thing. Because logistic regression, as I showed you 3 classes back, also learns a line, right? But the question is, which line will it learn? And the answer to that is perceptron or LR choose, right? Is that it will learn the line which it arrives at first in its minimization. Because once it gets to a line, right, after that, there is no reason for it to move. Because it is getting let's say this is the line that it gets to. After that, it won't move because there's no reason to move at all, right? Because that it is giving a 0 training error. So if it goes from here to here, it's the same error. So why would it move, right? Because if you remember, the way gradient descent works is that you get a W that gives you a minima, right? And after that, since there your gradient is 0, then you don't update at all. Then you converge. Right? Which means that it will give you one of these lines, but it will give you the one that it arrives at. So maybe it depends on what you initialize things with, or simply whichever it comes to, right? So if you think about this, right? So this W has 2 parameters. So you can, so this is W0 and this is W1, right? So you could create an animation, or maybe I'll create it for next class, is that this is your data, right? What will happen is that if you run gradient descent, it will start somewhere. Let's say you start here. Let's say you initialize your W vector at 0, 0, right? Then in the first iteration of your gradient descent, this will move somewhere, right? In the next, it will move somewhere. So every time what is happening here on this side is that there is a line which is just here. Then it becomes something like this. Then it goes like this. It goes like this. And then at some point, what will happen is that it will stop here, which is let's say this line, right? Now let's say this line in this space is over here, right? But there is no reason for logistic regression or perceptron to jump here, because both of them are giving you zero error, right? So it turns out that in perceptron or logistic regression, there is no sort of reason for them to move, okay? However, it turns out that there is one particular line that we like more than others for generalizability purposes. Any questions so far? I didn't ask, but okay. So what is the best boundary, right? It turns out that the best boundary, let's see, okay. So that's the question. So we want to find what is the best boundary. And what people have figured out is that the best boundary among all of these, all of them are giving you zero error, but the best boundary is the one that separates your data the most, right? So let's go back into our example. So let's say this is our some data, all triangles and all circles, right? So this is one correct line that could be learned by a perceptron, and this is another line that could be learned by a perceptron, right? It turns out that this line, right, because it is right at the middle of the separation, will give you a better generalizability than this line. Okay, the reason for, and we'll look at the exact reason. I mean, this is a topic of research, but the reason is that this line, since it is sort of right smack in the middle, I mean, I'm giving you an intuitive reason, is that when you're looking at test data, right, in the test data, even if you get a point here, a blue point here, right, because there's no reason to believe that blue points will only be here. There could be something that you missed in your training data, right? This one will still classify it as a blue point because it's on the other side, whereas this line would misclassify it, right? So the idea is that if you stay in the middle, right, while ensuring that your training error is zero, then it will give you a better generalizability. So there's less chance of making error in the test case. So this gives us a way to, or at least sort of a subjective way to figure out what is the better line. Is this is the better line than this one because it's separating the data more. But geometrically you can actually specify it. So the idea is that whatever line you have, right? So you take a parallel line and draw it to the closest positive point and closest negative point, right? So you cannot go beyond this or beyond this because then you will not be able to minimize, you have a zero training error, right? So this is what we call the margin. Okay, so a classifier which can maximize this margin is the best classifier. Okay, whereas a classifier or a line in which the margin is maximized is better than a line in which the margin. So in this case, the margin is going to be this because this is the smaller value. So margin has to be symmetric on either side, right? So this is smaller than that one. So if you can maximize your margin, then you will get better generalizability. Okay, so we'll look at it more sort of analytically next time. But intuitively, the idea is this, that if you can ensure that your line is smack in the middle, you will get, there will be a lower probability of it making a mistake in the test case, right? However, logistic regression and perceptrons do not ensure that, right? Because in their whole formulation, there is no place where they're saying, let's try to maximize the margin. All they're saying is, let's try to ensure that our training error is minimized. Of course, if you do regularization, that maybe you're also trying to minimize the complexity, right? But they're not explicitly talking about the margin. The classifier that we'll look at now, which is support vector machine, explicitly does that. So it essentially tries to learn the line which not only minimizes your training error, but also maximizes that margin. All right. So next class we'll see how to do that, because now our objective function will change. It is no longer just a simple loss function that we want to minimize on, or a likelihood function, but it's going to be a little more different. And it is going to pose some challenges in terms of the optimization. So we'll look at a new way of doing optimization, which is called quadratic optimization. and see how that works. All right? Any questions? Cool. Thank you. I'll see you on Friday. If you have not submitted your project report, you can do it now. And then Jin is going to take it after this.